to teach you about fully managed. You probably already do know what they are, you just don't know them by that name. All right, let's get started. So quickly, just to cover off what I plan to discuss in the next 40 minutes. First, I'll describe very high level about getting things done with distributed services, just to sort of frame our conversation. And we'll talk about two common coordination patterns we see with getting services to communicate with each other. Those are called choreography and orchestration. Then I'll illustrate how to orchestrate services using state machines. I'll introduce you to AWS Step Functions, which is a fully managed service that we offer that lets you run state machines in the cloud. I'll give you examples in the real world of customers using AWS Step Functions to orchestrate services, and then I'll teach you where to learn more. Okay, let's talk about getting things done with code, with services, how things work at a very high level. So in a monolith, everything gets deployed together, right? And so in this slide, I've made a bunch of colored boxes to represent what might be different modules of your application. And the gray bar underneath them all would be like the data store, right? And so in a monolith, all of our code is packaged up into one artifact and deployed onto one service together. And they've got a common data store. And that's generally how most projects start out. But as things grow, you add more and more modules to your system. Eventually, you probably need to start breaking it out into separate services. And we often call that approach microservices, even if the services are not necessarily very small. So with microservice architectures, we split this big monolith up into multiple systems. And so each module that is clearly separated from each other module gets its own data store now. And the advantage of this, each of these being their own services, is we get increased agility and scalability. And let me explain what I mean by each of those. So I'm talking about agility here. What I mean is now teams can focus just on one vertical slice, right? One service now, instead of having to think about how what their work is doing on that service connects to all the other modules, because they've already been separated out. That means that code can evolve. You could use different languages to implement these different slices of services. And also teams have their own data store, so they don't necessarily need to worry anymore about having schema changes impact other modules in the larger system. So that generally lets teams get things done faster. You also get better scalability because with microservices, each service can be tuned and scaled appropriately. And that might be some vertical scaling, as indicated by these larger colored boxes, or it might be horizontal scaling, or sharding, where you have multiple copies of a particular compute process and maybe behind a load balancer or something. And even the databases can scale and even be different types of data stores to serve each service's specific needs. And so that's really great. Microservices tend to give us a lot of value, but it's not always all 100% roses in microservices land. Because big distributed systems, they get harder to coordinate and harder to debug. As these systems need to work with each other to get larger amounts of work done, specifically with workflows, it can be hard to figure out when something doesn't work, what was the problem? Where did things fall apart? You also might need to wonder about, how do I make these services communicate with each other? Should they be totally distributed, where they all just communicate via some shared message bus and they don't know anything about each other? Or maybe when a process needs to get executed in a particular workflow, maybe that should live in one place and all the other services should get invoked accordingly to that process. These are two opposite style approaches to service coordination, and they're both useful. And so we'll talk about both of them in turn now. First, let's talk about choreography, and then we'll move on to orchestration. So here, to talk about this, I always like to get a little bit more concrete and give a specific example. So this is a very simplified banking system, but I picked this subject because it's something we can probably all relate to. You might have things start out with an application. I would like to open a bank account. So I fill out some kind of application. And that might be handled by this blue account application service. Now, to process the application, maybe we have a data checking service, which will do things like check the identity documentation I provide for my account application, maybe also check my address to make sure it's formatted correctly and is it actually a known place. And then if all of that looks good, then I should have an account created. And we can zoom in here to look at that. We're not going to talk about the rest of this system. I just wanted to contextualize it, right? In this banking system, you'd also have the ability of, debiting and crediting accounts and transferring funds, and some BI layer, business intelligence layer at the bottom that might be observing events from all of these systems to give you more insight. But we can just zoom in here and say, to open my bank account, this is the flow, right? These are the collaborating services that need to exist. And probably I want to insert some human review step in here. So if the identity check or the address check comes back flagged by the data checking service, then I might want a human to step in and review the application. But maybe for my simplified example, I'll say, if everything looks good, we don't need a human to review. We can just approve the application directly and get an account created with the account service. So in choreography, we use this term to describe services emitting events or publishing events about things that happen in their service that other services might want to know about or react to. And that's it. It's very, very decoupled. You have an event bus or some kind of pub sub or messaging relay system that all the services can listen to and be notified of events that they care about. And these services will work in concert to achieve some larger flow simply based on what events they emit and what events they listen to then react to. And in that way, a whole sequence of events can correspond to a larger workflow getting executed. And so here's how that bank account workflow might happen here with choreography. I would submit my application, and we would start out with the account application service emitting an application submitted event. And then, because we need to have my identity checked, we need to emit this identity check requested event. The data checking service would listen for that event. It would do an identity check. Then it would return an identity checked event. The account application service is interested in that event, so it would be listening for that. And after it got the result of that, it would go and check the address. Of course, the same flow would happen. The data checking service hears that an address check is requested. It's going to perform that address check and emit the results back with an address checked event. The account application service is interested in that. So now it knows that the identity was checked and the address was checked. Then it all about might come onto this event bus and that they should react accordingly. And so even though they're distributed this way, there is still a coupling. There is still an awareness of events. They need to know what events each other emits so that they know which ones they need to react to. And the decoupling of this is nice, but as you can see, it does feel a little bit complex in order just to implement a relatively simple workflow here. And so there is an alternative. The alternative is something we call orchestration. In orchestration, you've got one place or one process that manages the state for your workflow, and it's just going to call the appropriate services in turn. For example, in the account application service, that would probably be where something would be responsible for ushering the whole flow of an account application. It would check the identity. It would check the address for an applicant. Maybe it would get a human involved in a review if needed. And then ultimately, if everything was good and an approval decision was made automatically or by a human, it could get the account created. And that's a much simpler workflow, as you can see. And this is probably the way that's more familiar to us because we're probably programming like this already just by writing a bunch of if-else statements in our code, coordinating with other services. And that's fine, but there's a way to get things even more robust. So before I explain how, let me just cover off when should you use choreography and when should you use orchestration. Well, based on what you've seen, you can probably agree that choreography can get quite complex pretty quickly for workflows. And so you only want to use a choreography style, fully decoupled approach where they're just reacting to events for simple workflows without much logic. Or a better piece of advice might be to think of it as use choreography for broadcast style workflows where a service no longer depends on what the other services will do once it emits a particular event. You can think of it like fire and forget. For example, a nice scene might be for the account application service to just emit application approved, and then it's done. And then you could use choreography to have the account service react to that one business domain event in order to create an account. But we didn't need to implement the whole workflow in a choreography fashion, right? You can just glue separate systems together with choreography at the point where a nice clean handoff might happen. Whereas orchestration is designed to do well at this idea of managing workflows. And you should use orchestration because you'll typically get some kind of execution auditability for your workflow. What I mean by that is because it's all managed in one place and all your business logic is in one place, it's easier to keep tabs on the flow of a particular execution of that workflow and understand what the ins and outs from each system are that you're collaborating with, and it makes it easier to debug. You'll also generally get better retries. On what you saw before in the sample flow. So this might be what our workflow looks like. We start by verifying my identity documents for an application. We check an address. Then we decide if we want to get a human involved in a review. We're going to wait for that review to happen if the review does happen. And then finally, the application will get approved. And that's nice, but there are some things about this workflow that we can improve. So let's evolve this a little bit more. First, this step, verifying identity documents and checking addresses, can be done in parallel. We don't need to do them in this serial fashion because checking the address has no impact on, it has no dependency on the identity document results of that verification. So we can arrange these in parallel instead. So now what we're saying is start my workflow, immediately in parallel, check an identity document and check the address. They don't depend on each other. Just get both of those things done in whichever order it happens. They can happen at the same time. Wait for both of those results to come back to me, and then I'll have the information I need to decide if a human review is required. But because we can do those steps in parallel, we've sped up our system a little bit. Next, we can look at this step and say, well, a human review isn't always required, right? It's only going to be required for, in this example, if one of these checks, the identity document verification or the address check, comes back with some sort of flag from that service. And so in those cases, we'll want to wait for review. But if neither one of those previous checks gives me a flag, my simple example is going to say, fine, let's just approve the application. So let's change this workflow to reflect that. And that's it. It's a minor change, but now we can see that it's possible to go straight from the review required checking process to say, do I need to have a human get involved or not, to straight to approved. Finally, we can look at this and say, we don't always approve applications, of course. Sometimes an application might be rejected because a human being looked at something that got flagged and finally decided, no, I don't want to approve this application. So we need to add that into our workflow. And so that's what we've done now. So we've added a step that says, after we get a review, we'll look at the result of that review and see if it was an approval or rejection. And then correspondingly, we'll either approve the application or reject the application. And that nicely sums up our entire example bank account workflow. It's a much nicer evolved workflow because we're taking advantage of parallelism. We're waiting, but only when we need to. Now, this, what you've just looked at here, drawn out on the screen, is actually something called a state machine. And that might be an unfamiliar term to you, but you're already familiar with this. You just don't know it, right? We already use the concept of state machines in our programming sometimes, even if we don't explicitly codify it as such, because really, a state machine is quite simple. State machines just describe a collection of computational steps that we're splitting into discrete states, right? So in code that we're writing sometimes when we're working view, etc., right? So with if, else, and switch statements and whatnot, or one starting state, and they've always only got one active state while they're executing. And what happens is the active state gets some input, so that'll be the first state at the beginning. You're going to start your state machine by giving it some input. It will take some action using that input, and it's going to generate some output. And then based on that output, the state machine decides what's the next state that I go into. And the state machine just transitions from one state to the next based on these outputs and the rules that we define. And ultimately, work is getting done and moves us into a successful execution, or we hit some error that we don't know how to recover from, and we end up with a failed execution. But that's it. That's a state machine in a nutshell. And the cool thing is we have a service that will let you run state machines in the cloud in a really nice fashion. And it's called AWS Step Functions. It's a fully managed state machines on AWS. That's the way I like to explain it to people. You can also think of it as a way to have resilient workflow automation, running in the cloud at scale. What's great about Step Functions is because it's fully managed, we at AWS handle the high availability and the scalability concerns for you. You just define your state machines and you tell us to execute them. You give us input and say, execute, start this execution on this state machine with this input, and we'll handle the availability and the scalability for you. And we've got built-in error handling with Step Functions, which I'll talk about more later, as well as powerful AWS service integration to implement these workflows, tying in to a lot of existing AWS services to make your life easier. We also have first-class support for integrating with your own services. Now, when I first heard about Step Functions, before I even worked at AWS, I thought that maybe that was only for managing like AWS Lambda functions, right? Or the idea of code as a service, right? The serverless functions, but it's not. You can use Step Functions to help automate any process that's running anywhere. You can implement any one of these tasks that comprise a workflow in your own server on premises, even on a mobile phone, anywhere that can pull the AWS Step Functions API over HTTPS can act as a process to handle tasks in a workflow, which is pretty neat. And also, to help with the sort of debuggability and explainability of workflows with distributed systems, Step Functions makes it really easy to audit every execution history, and you get a nice visual monitoring to see how workflow executed in what path, and you can see each step, what the inputs and outputs were for each state in the workflow. And we'll see details about more of that as we go along. Let's talk about the basics of Step Functions. Here's how Step Functions works at a very high level. As you've already seen, we coordinate our individual tasks into a visual workflow. And these workflows that we build are a number of steps, and these steps are just called states. And all of these states together makes a state machine. Now, the most common kind of state, or the most useful kind, because if you couldn't do this, you couldn't do anything, is the task state. And that's what does work. And that work can either be coordinating other AWS services, or it can be working in concert with a process that you can host anywhere, as I already explained. There's a pass state, which just passes your input straight through to your outputs. That's very useful for when you're just starting to edit a state machine at the beginning. You can make all of your states just pass states so you can sketch out the flow. And then you can change each of those states later to whatever the appropriate node type is. We also have a state called a wait state, which will wait for a particular period of time that could be relative or absolute before continuing. So effectively, it pauses execution until some future time. You have parallel states, which can branch off execution and effectively do many state machines inside your larger one. And this is also within inside one AWS Step Functions state machine definition, but then the definition can nest inside, which is very helpful for getting work done in parallel. And you've got choice states, which can look at output and decide what state do I go to next based on the state that I have in the output from my previous states. And when these state machines are executing, we're just moving from one state to another. We call those transitions. And finally, a nice point, a cool thing about using step functions is that by creating your states in very focused fashions, you can reuse the same task states for different workflows, giving you really nice code reusability. How does this all work? It uses something called Amazon States language, which is a fully specified language that lets you express your state machines using some nicely structured JSON. As you can see here, at the top level, you can have comments, and you define what state your machine should start at, and these are just names. We have a state called Hello World. And then you have one or more states defined inside that states key that describe different types of states, which you already know some of the types of, and how they glue together in order to sketch out an entire workflow. Let's look at this in more practical terms. Here's our example new account workflow with our diagram on the right. And let's illustrate these different types of states inside of this workflow. We're going to talk about tasks, parallel steps, branching choices, and even waiting for a callback. So performing a task can be done in a number of different ways. You can call an AWS Lambda function to do basically whatever you want in whatever language you want. And you're only going to get billed for the amount of time that code is being executed. That's nice. Or you could wait for some polling worker to perform some activity. And this is the mechanism I explained before, where you can have code running anywhere that fulfills a task step in a state machine. Finally, if you want, you can pass parameters to an API of an integrated AWS service to get some work done. In this example, if we look at just this section here for verifying identity documents, we could implement this by calling a Lambda function. And this is the Amazon States language we might use to implement this task. So we give it a name, verify identity documents. We say the type is task. This task has some parameters. And then I point to a resource, and that resource is an Amazon resource name pointing to the Lambda function that I want to run to implement this task state. And those parameters that I'm defining are going to be the parameters that get passed on to the Lambda when the Lambda gets invoked to do this work. And you can see a little bit of a naming convention here where we use this $sign on each side of a key value setup in order to say, this is how I want data from my state machine state, in this case, an application object that has a name and an ID doc as 3 path attributes, how I want those to thread through in the parameters to the Lambda. And finally, in this case, there's only one step inside this branch of this parallel execution, so it says end true, because there are no other branches there for that parallel execution that this particular task step lives under. We can also execute branches in parallel, like we were just looking at. The verifying identity documents was one branch that we were executing in parallel. And this just contains an array of state machines to execute, and we get back an output of array elements describing each of the branches that executed. So in practical terms, here's how we would implement both parallel branches here for checking identity documents and checking the address. It looks very similar, except this time the type of this particular state is called parallel, and we have a branches property that define little state machine JSON snippets inside. So it's like the larger JSON, but just you can use that same structure inside each branch of a parallel state in order to get work done. And we can say that the result for all of these different branches, we want to end up in a variable, in this case called checks, inside the larger state machine state. And the next step would be human review required. That's the name of it. And we also want to make a choice. We want to look at data and decide what step do I do next. So this is like a switch statement in programming. It looks at an array of choice expressions and it compares variables to values and decides what's the next state I should go to. So here you can see that our human review required state is a type of choice, and that's the state type. And we have an array of choice expressions that look at particular variables. In this case, we're looking at things from the checks variable, which came from our previous state. And we'll see if either one of our checks was flagged, then as true, then we want to wait for a human to review. Otherwise, we'll default to approving the application. Finally, in addition to just waiting for a fixed period of time, oftentimes we might want to wait for a callback. We might want to wait for a human to get involved in this process, do something, and then continue onwards. And so we can use this concept inside state machines of a task token to do this. So with the callback interaction style, we have step functions, create a task token and pass it on to some other service. When that other service is done with its work, it calls back to the step functions API using a send task success or send task failure API call with the task token, so step functions knows what that service is talking about. And then the workflow will resume its execution appropriately. Here's how invoking that might work here with an external callback from a Lambda function. So what we would do here is we're going to say that the type is task. The resource is a special ARN string that says, I want to invoke a Lambda and wait for a task token. The Lambda will, in this case, I'm calling one called flag application for review. I'm giving it some payload. These are the parameters to go into the Lambda function execution. And you'll notice that one of those is this task token that comes from the step function state. And in this case, what this flag application review Lambda would do is store that task token in a database somewhere for that particular application ID. And then a human would have some interface where they could see all of the applications that were flagged. And then when they made a decision on it, at that point, whenever they interacted with some API, it would get that task token from that pending application that was flagged. And it could then call back to the step functions to say, here's the result that the human took when they clicked approve or reject. And then the workflow would resume executing. Okay, let's dive a little bit deeper into step functions now. I've already covered most of the state types. There actually aren't that many. Step functions is a pretty simple service once you understand the base concepts. You have seen most of these state types already, except for a few. I've talked about the wait type. Even though you didn't see it, you understand it lets you wait for a particular period of time. The map type is the most interesting one we haven't talked about yet. And this lets you process an array of input elements with a particular state machine. This is very similar to, in programming, you might be familiar with a map function, which takes a function and an array of items and applies that function to every item in the array to get back a new array of results. That's the same thing that the map state here can do in step functions. And what's neat is you can even coordinate the amount of parallelism you want in that map execution. So you can actually say, do them in one at a time, or you can say, I'm happy to have parallel execution, and you can set the maximum number of parallel executions, or say, do them all at once is fine. But this is different than the parallel state, because a parallel state says, do different things for this input, whereas the map state says, do the same state machine for each item in this input. And finally, the only other steps we haven't talked about yet are succeed and fail. Succeed just is used to semantically mark the successful end of a branch of a parallel or an iteration of map. And you've also got a fail state, which says explicitly something has gone wrong, terminate the state machine, and mark this execution as a failure. We integrate with a number of AWS services with step functions. I don't have time to talk about all these right now, but as you can see, there's quite a bit here. And what this means is that these are all the APIs that you can call directly from a step function task if you would like to. Working with step functions is really quite easy. As you've seen already, we define them with JSON. And what's neat about this is in the web console, when you write your step functions with that JSON, you get back a nice visualization of what that state machine looks like. And you didn't know this, but those earlier diagrams you saw, those were already done with step functions. So that's why this diagram at the bottom might look familiar to you, because we've already been using step functions to create some of these slides. And finally, my favorite feature about step functions is that you get to monitor their execution. So every time one of them runs, while it's running and then after it's running, you can go and see what steps ran and what were the inputs and outputs for every step, which makes debugging, especially complex workflows, really easy. Of course, things go wrong sometimes. And Step Functions knows this and gives you some really nice capabilities to handle retries and errors. So you can have failures happen because of timeouts, or maybe a task failed for some reason, or you might have had insufficient permissions to execute a particular step. Now, tasks can retry when errors occur using a back-off rate that you specify between retries up to a max number of attempts. And of course, if you exceed the maximum number of retries, or there were no retries that you defined for a particular step, you can catch these tasks for specific errors and transition to other states as appropriate. So there's really nice retry and catch semantics there for you to use when you author your state machines. If you want to do some development with step functions, here's some things I recommend. Check out Step Functions Local. This lets you execute a version of step functions on your own system, which can make debugging your workflows even easier, and certainly can speed up some of your workflows that way. So I recommend that. There's a binary called statelint, which will look at your JSON for your step function state machines and tell you if there's anything wrong with them. If you like using the serverless framework, there's a plugin that knows how to handle step functions really well. And finally, if you're like me and you like writing in Visual Studio Code, there is an AWS Step Functions constructor extension, which lets you write your JSON for your state machine and get a nice live preview on the right-hand side of your editor, seeing what that step function state machine looks like, similar to what you'll get with those circles and arrows in the console. But you can have that locally while you're authoring as well, which I really like. Okay, so step functions and actions. Let's talk about some real-world use cases and customers that are doing cool things. So the Guardian News and Media Group, they've used step functions for a lot of things. I'm not going to read this whole quote to you, but it's by Paul Brown, a senior developer manager at the Guardian. And he mentions that step functions gives them reliable and automated ways of orchestrating complex queries and processes between their distributed systems, giving them more productivity and agility. And another benefit is it makes it easier to discuss solutions with non-technical stakeholders, because again, when you explicitly codify these things with step functions, you get a visual representation of that workflow. And that makes it easy for people who are not coders to understand what we're building. Here are a few of the actual services or solutions that have been built by the Guardian using step functions. They automate subscriber account deletions across many distributed systems. They can now receive customer orders while external billing and payment services are offline. And they can run ETL workloads for a newspaper fulfillment pipeline through a series of Lambda functions. These are all very common benefits and examples of cases where step functions really shine. Now, let's talk about the Coca-Cola Company for a minute. I don't have time to go into the detail of this, but you can watch them talk about it themselves. There's a YouTube link here on this slide. But every time Coca-Cola needs to make a nutrition facts label, and they have many products, so they have to do this a lot, either because their formulations change or because the label design changes. They have a workflow where data has to go through a number of steps, ultimately generating this nutrition facts label. It used to take them 36 hours to go from a change to a finished and approved label. Using step functions, they were able to cut this down to 10 seconds. That's a huge increase in efficiency. And a lot of that efficiency actually just came from this point I brought up before about being able to use the visual representation and debuggability of these workflows to help hone in on problems quicker. As you can see, the benefits they cite here were performing data validation and transformation steps with a visual workflow to help non-technical people understand it. And then as they were actually running these workflows, they could look in real time and see where they were behaving appropriately, because step functions makes it so easy to trace that execution. And that'll let you even identify problems and optimize things on the spot instead of having to troll through a lot of log files later, for example. The key benefits of step functions, to wrap up: it's a fully managed service, which means we handle the high availability and scalability of it for you. The visual monitoring and state management that you get is top-notch and makes debugging and understanding how your services are getting coordinated very easy to do. It also gives you this auditable history of each execution, which may help you from a regulatory perspective if you need to prove exactly what all the ins and outs were for your service coordinations in order to meet some regulatory requirement. Built-in error handling is really robust. And finally, step functions is pay per use. And the billing model is really neat in that the billing model is based on how many state transitions your state machines go through. It's not based on time a step function takes to execute. And what's cool about that is if you have a wait step, and that wait step says, I want to wait for, in this case, it supports up to 1 year. So step functions can have up to 1 year of waiting time. You're not billed for any of that time. The step function just pauses and waits for it, and you're only billed for the state transitions. That's really powerful and can be very cost effective for a number of use cases. There was another use case by Coca-Cola that I didn't talk about where they leveraged that to great effect. So if this has excited you and you want to learn more about how to use step functions for your own modern application development, here's what I recommend. Start by looking at the Create a Serverless Workflow example online. And after that, spend a little bit of time and just read the entire Step Functions developer guide. It's not that big. As I explained, Step Functions is not actually a very complicated service, but it's very powerful. And I think it'll take you about 2 hours if you want to read the whole developer guide. And then you'll have a really good understanding of all the moving parts. And finally, if you'd like to see examples of Step Functions in action, we have a number of reference architectures you can look at the URL on this slide in order to see more. So that's it. I want to encourage you to continue your modern application development journey by looking at the AWS training and certification resources we have available. There's a lot of stuff out there online that we make available for you. It's definitely worth your time to check out. Keep in mind, we have an AWS Certified Developer Associate exam, and we also have a Certified DevOps Engineer Professional exam. Those are really great to help prove your knowledge on AWS topics. And finally, I personally want to thank you for taking this time to attend this webinar. It means a lot to me. I know you could be doing a lot with your time, and the fact that you chose to spend the last 40 minutes with me is really great. So thank you so much. I hope you found it useful, and please do fill out the survey that we're going to show you, because that's what helps us continue to iterate and give you the best content possible. Also, please keep in touch with me if you like. You can find me on LinkedIn or Twitter at the handle there on the screen. It's just my first and last name all smushed together. Okay, I hope you have a great day wherever you are.